And now she is a professor at the Geomar Helmholtz Center in Kiel in Germany, as well as at the China University of Geosciences in Wuhan. So is a veritable Earth scientist, I would say, looking at her object of study, the Earth, from all different angles, and working actually on different tectonic plates throughout her career. In her research, she's investigating the lithosphere. So this is, I guess, the Earth crusts and the upper regions of the Earth mantle, so the rocky shell of our planet, and how it changes over time. In particular, its chemical and thermal properties. And actually, to cite from the announcement of the Augustus Love medal she was awarded last year by the European Geoscience Union, was her integrated models of the lithosphere helped reconcile the conflicting views between geophysicists and geochemists. So her work is truly interdisciplinary. And this is also evidenced by her book that she wrote, which is called The Lithosphere, an Interdisciplinary Approach, which is considered an authoritative work in the community. Besides her research, Irina has been an integral part of the scientific community as a journal editor and currently as the president-elect of the European Geoscience Union, as well as the co-founder of a company that shares her expertise in geoscience with industry. And now I'm very excited that she will share her expertise with us and tell us about how it is to be living on a living Earth. So let me start.
Thank you, Volker.
Start the video.
Good afternoon, everyone. Thank you very much for a nice introduction. I feel very much honored to be invited to this international meeting. It is an excellent idea to collect scientists working in various physical disciplines to highlight the results and importance of female research in physical sciences. I was asked to say a few words at the very beginning about myself, and this slide summarizes my background. I am a theoretical solid earth geophysicist, largely working on global processes, but with deviation to regional studies as well. I have worked in several European countries and United States, and now I'm affiliated with academic institutions in Germany and China. During my research, I have been honored by the award from the European Geosciences Union, and I was also elected to the Academia Europaea, Royal Danish Academy of Sciences and Letters, and as a Fellow of Geological Society of America. I have also been elected last year as Vice President of the European Geosciences Union, where I will start as President in the coming spring. This talk is a very general one, and I was hesitating how to title it. So I decided to give a very generalistic title, Living on a Living Earth. And I would like to start with some definition of what is a geophysicist. It goes back to 1957, where it was published by the professional journal in geology and mining. And they defined geophysicist as a subject producing with a vigorous fortitude endless rows of incomprehensible equations derived with a microscopic precision from vague assumptions based on questionable data obtained in inconclusive experiments performed with non-calibrated instruments by unreliable persons with questionable mental abilities. So I hope that this sets up the scene, and I'll try to make my lecture very much general so that hopefully each of you will find something interesting and something unknown to you, and there will be something for you to discuss with your colleagues and to think about. So this is a brief overview of my talk. I'll start with some basic information on the Earth's deep structure and historical perspective on that. Then I'll discuss plate tectonics, how one can make new plates, how one can create a new ocean, and what the interaction between the lithospheric plates and mantle means for the climate and for the changes in our environment. And finally, I'll add some words and some illustrations on how the lithospheric plates are recycled and what it means in terms of mineral resources. To start with, I want to show some very generalistic textbook level slides about the Earth's deep structure. So the Earth has a late structure. So we speak about the planet, which in big simple terms has the radius of almost 6,500 kilometers. And the structure is includes several shells with mantle on the top and core at the bottom. And all of this is obviously very heterogeneous. The major boundaries between all of these different shells have been discovered starting from the late 19th century, actually very fast, within something like 40 years. But it is important that all of these observations, which came from geophysics, had a very, very good foundation in well-developed by that time physics and mathematics. So that with all of the equations known from, for example, optics, wave propagation, it was easy to employ them in understanding, for example, seismic observations for the deep Earth. So these are all of the most famous names, which their contributions and the years of these contributions. And it's not a big surprise that there were no females, because the science at that time was not populated by females. The only name which is here is the one which I cannot skip, because this is the Danish scientist, Danish seismologist by the name Inge Lehmann, who is the discoverer of the Earth's inner core, which was termed the Lehmann discontinuity, very deep in the Earth at more than 5,000 kilometers depth. And in one of the interviews, she wrote about herself that she was the only Danish seismologist. She lived an exceptional life and lived extremely long, for almost 105 years. And she was a very shy person. So she's worked most of her life in the seismology department of the Danish Geodetic Institute, where she retired at the age of 65. Most of her life was at the same time as Niels Bohr was active. And this had some impact on her awards and honors. And I found this photo, the photo of her gravestone of her father and herself. Apparently, this type of monument was designed by herself, because, as I said, she was a very shy person, and you can see the environment where it is located. It looks simply like a very forested area. So she's mostly famous for discovering of the Earth's inner core. I will not go into any specific details. They are written at the bottom for those who are interested. But in simple terms, by that time, it was believed that the Earth core is liquid, which put limitations on how the seismic waves can propagate through it. And she discovered the waves which were not supposed to be there. So she published, based on these results, an article with the shortest title, P, because this is the name of the waves, seismic waves, which she observed, primary waves, P waves. And her discovery has not been confirmed until it was supported by the computer calculations in 1971, 35 years later. And for this discovery, she got the very prestigious medal from the American Geophysical Union. At the award ceremony, the person, a very famous American geophysicist who gave the citation, said about her discovery that it was discovered through exacting scrutiny of seismic records by a master of a black art, for which no amount of computerization is likely to be a complete substitute. As I said before, she had received quite a number of awards and honors, but not from the Danish. She has not been elected as the member of the Royal Danish Academy of Sciences. And the reason for this is that Niels Bohr, who was at that time president of the Academy, was opposed to have females in the Academy. The first female who was elected was Madame Curie. That was in the 1920s, but Madame Curie has never come to the Danish Academy in person. And the second female was elected to the Academy only after the death of Niels Bohr. That was in mid-60s. And this is like a historical anecdote, because when this female was elected to the Academy, the first thing the Academy had to do was to build, sorry to say, female toilets, which didn't exist at that time. But Inge Lehmann has never been elected to follow the pattern established by Niels Bohr, but she got, as I said, a huge number of different awards. There is the street, which is named after her in Copenhagen, and in 1997, the American Geophysical Union has established a very prestigious Inge Lehmann Medal for the outstanding research in the deep earth. Now let's go to plate tectonics and the lithosphere. So we spoke about the entire structure of the Earth, but the lithosphere forms only the upper 100 to 300 kilometer thick layer of the Earth. One should remember that it is a very important layer because it has a dual nature. On one side, it reflects and sort of sees what is deep in the Earth below, which is related to convective patterns in the mantle. And on the other side, it is also provides the view from the top, which is plate tectonics view. And this relates to rigid behavior of the lithospheric plates when they're involved in the plate tectonic motion. This provides a really dual nature of the entire phenomena with very diverse observations, which combine both what is coming from the convection and what is coming from rigid behavior of lithospheric plates. One of the outstanding questions in geophysics is, when did plate tectonics begin? And there is no answer to this question up to now. So the estimate cover basically well, something like 75% of the age of the time of the Earth, ranging from almost the time when the Earth was created, about 4.5, 4.4 billion years ago, and up to the age which is as young in geological terms as only 800 million years. So there is also a big debate if plate tectonics is a continuous process or if it is an episodic process. And this is an example of one of the papers published 5 years ago, which actually suggests that first there was stagnant plate convection, then there was protoplate tectonics for some period of time, then again to switch to stagnant plate convection, and the plate tectonics is really very young phenomena on the Earth. Well, it is plate tectonics which produces continents and oceans. And this slide illustrates two end-member cases. One is for the Earth, where plate tectonics is surface manifestation of the mantle convection because the Earth is cooling. And it is the most efficient way to remove the heat from the planet. And characteristic feature of this is, as I said, the existence of continents and oceans. They have different topographies, all of you know, and this is exactly the cause, the manifestation and cause of plate tectonics consequence. Sorry. If we go to Mars, Mars has quite non-uniform distribution of topography in the northern and southern hemisphere, and it is assumed that it may have had plate tectonics during the first maybe 1 billion year after its formation. The Venus is a different case. The Venus has no plate tectonics at present, and it is what is called stagnant lit convection. It means that there is only one top layer which makes one planet scale plate on the top of mantle convection. And the problem here is that the age of the surface is only 600 million years. It is much, much younger than the age of the planet, which is similar to the Earth. And what happened at that time, 600 million years, was that the entire surface was destructed by a mantle or return. So we simply don't know if plate tectonics could have existed at the early stages of Venus development, but it doesn't exist at present. And what is important for plate tectonics is that it requires the presence of water in the mantle because it provides lubrication for subduction. So since I mentioned continents and ocean, another important name of female geophysicist to mention here is Mary Tharp. She is an American geophysicist. Actually, she has never been employed as a geophysicist. She was employed as a draftsperson based on her education and her family background. And she was employed in the Columbia University of New York together with the young scientist at that time, Bruce Hisen, who was collecting geophysical data, and she was interpreting this data and producing the maps, topographic maps of the ocean floor and all the ocean bathymetry. And it was definitely a very successful combination of people, and they worked together with the Austrian painter Heinrich Baron, who helped them to produce the most famous and absolutely iconic map, which was termed The Flow of the Oceans and which was published in 1976. And you should bear in mind that despite it is iconic map, and everyone is still considering it as an absolute masterpiece, not only of the arts, but also of the science which went into it. It was skeptically accepted by their community at the very beginning, because it came out more or less at the time of plate tectonics, when plate tectonics was being established, and there was far too much of intuition and generalization which went into this map, but all of the later studies documented that it is a very, very accurate map. So the major features here is the presence of mid-ocean ridges, which go around all of the oceans, and then all of this big mass in the Western Pacific is also present in other places, and it illustrates the complications which are coming from mantle convective instabilities, for example, like observed in Hawaii, Canaries, and other places. So let me first start with some basics of plate tectonics to those of you who were not very much curious about the subject before. So it is believed that, and it is fully accepted, that the new lithosphere is created at mid-ocean ridges due to the spreading. So this map on the right shows the distribution of ages of oceanic lithosphere. Everything which is red refers to mid-ocean ridges. And you can see that actually the speed of spreading, the rate of spreading is different in different oceans. You have this band very broad where the speed is very fast, and you have it very narrow, for example, in the South Indian Ocean, when the spreading is very, very slow. And there are also peculiar places on Earth, for example, like in Iceland, where mid-ocean ridge crosses the island. And it's also peculiar that the unusual nature of this place has been recognized since very old times, so that it was used as the site of an ancient parliament. So the lithosphere is not only created, it is also destroyed, and it is destroyed at the subduction systems. So the most famous example is around the Pacific Ocean, this red band, which shows subduction systems which are associated with a lot of seismicity, and many of the tsunamis generated there. And how do we know about this? We know this in particular from the images which come from seismic tomography. And they show these blue bulbs, which are associated with fast slaps, which have cold temperatures, and this explains why conventionally this color code is used, that blue typically stays for cold regions and red stays for warm regions. Please don't think that the Pacific Ocean is unique. If you live in Europe, you should also be aware that numerous subduction systems exist in the Mediterranean region, and this is the example of 4 of them. And you see that the pattern is very, very similar. Another important issue here is that not all continental regions margins have subductions. So, for example, the switch between the colors corresponds here on this map to different tectonic plates. So you can see that you really have plate margins around, well, along the edge of North and South America, but you do not have them on the Atlantic side. So on the Atlantic side, the plate margin is in the middle, so that the nature of the margins in the Atlantic Ocean and Indian Ocean is completely different. From the other side, some plate boundaries may cross continents, and in this case, quite often they're not divergent. The best examples is the San Andreas Fault in North America, North Anatolian Fault across Turkey, and also the Dead Sea Rift. So this is an example of the Dead Sea Rift, and it is a plate boundary. So now switching to the new topic, how to make a new option. This very naive slide with the naive picture from textbook shows traditional explanation how you switch from continental extension, continental rifting, to ocean spreading and ocean drifting. And the classical example of this type is the Red Sea. So I highlighted here on this map on the left, in the red color, all of the plate boundaries, and you can see that there is a plate boundary which goes just along the entire Red Sea. So the opening of the Red Sea started first in the south, and then it started propagating to the north. And what we expect is that the Red Sea should be similar to mid-ocean ridges, so that we have the veiling of a hot mantle in the central part, and it should produce low seismic velocities, and we should observe them in seismic tomography. So this is our expectation. And this is our observation on the left. So the background color shows seismic velocities at the depth of 100 kilometers. Again, the color code is the same. Red is slow, blue is fast. Well, we expect that all of the red anomaly, which corresponds to uplift of molten mantle material, should be along the Red Sea axis, and we do not observe it. So that all of these anomalies are shifted towards the Arabian Shield by approximately 300 kilometers. And what is more peculiar, if we add to these geological observations, we also see that all of these yellow colors, they mark young magmatism. So it is also located not along the spreading axis of the Red Sea, but it is located within the Arabian Shield. So the question is, what does it mean? We performed numerical modeling, combining together geophysical and geological observations, and our results show that it is very important what was the pre-extensional structure. And it is very different in the northern part of the Red Sea and in the southern part. And because of this pre-extensional structure, in the southern Red Sea, the entire melting zone is located under the Red Sea axis, but in the North Sea, it is shifted towards North Central Arabia, and the melting is located where we observe these magmatic provinces at the surface. So our interpretation is that what is happening at present is that a new sea is being born in northwestern Arabia. So that this plot on the left shows how rifting propagated in the past. The black dots here show the distribution of seismicity. You can see that in the northern part, it is not really following the axial part of the Red Sea. And there is already the fault, which is similar to the Dead Sea Fault, which goes across the Red Sea, and it follows the pre-existing fault structure. So that what we believe is happening now is that the northern part of the Red Sea will not continue here. It will use this existing fault as Dead Sea Fault, and then it will continue spreading of the Arabian Shield in the northern part, and then it will merge with the Dead Sea Rift further in the north. Good question to ask, is this situation with the jump of mid-ocean ridge unique? If you look at this map from our THARP for the North Atlantic Ocean, you see how complicated it is, and you will be wise to start suggesting and thinking that no, it is not unique, that jumps of mid-ocean ridge do happen. So I plotted here how the extension of mid-ocean ridge was propagating in the North Atlantic Ocean. So it started further to the south much earlier, about 160 or more million years ago. Then it followed the present location of mid-ocean ridge, and then it went between Greenland and North America. And this is how the Labrador Sea has been created. What happened after that was that because of plate forces, this direction was not favorable, and then the spreading ridge jumped to the northern part of the Atlantic Ocean, and it went between Greenland and Europe, and actually between Iceland and Europe, until the new fault zone was created here where I'm showing, And then there was the new jump of the mid-ocean ridge, so that it started crossing Iceland and then started propagating further towards the Arctic Ocean. So we have this very complex structure. We still observe the existence of these paleo-spreading ridges. They are very visible in bathymetry. They have their own characteristics. So this is something which one can expect maybe happening in different parts of the globe. So since I have been speaking about Iceland, you probably know that, well, Iceland has lots of volcanoes, it's cooking, it's heating, and it's not very far from Greenland. So the question is there any effect between the processes which affect Iceland and which may destroy or affect the fate of the ice sheet in Greenland? Again, if you look at the map from Mary Tharp, I highlighted here the track of the Hawaii hotspot, so that Hawaii is now here, but it was moving this way. And you see all of these complicated features here, which show other hotspot tracks like Louisville and others. So now let's look in more detail what is happening in the North Atlantic around Iceland. But before we go to that, I would like to show you this quite peculiar result, which was published first about 20 years ago and then later in more detail. And what it shows is that our sort of intuitional feeling that once you start melting a big piece of ice, you will homogeneously increase sea level everywhere is incorrect. In reality, what it shows, so this is a result of numerical modeling for the collapse of the West Antarctic ice sheet. So it is here. So that what happens here is that some regions actually will be drying, will be going up, and other regions will be drawing down, and the water level will increase, so that in reality, the most affected parts, strangely enough, will include the North American cities. So you can understand, looking at this slide, how important is the issue and how important is the problem. So this is some summary of observations and data for Greenland ice sheet. And all of these many lines here, which I encircled in this red dotted line, show the proposed locations of Iceland hotspot tracks. They all cross Greenland. So you would expect that they should have impacted the melting of the ice sheet. And there are some publications which suggest that there is an increase in the melting of the ice sheet, but this is generalized over the entire Greenland. From the other side, there are also observations that there is something happening with the ice there around Greenland and also in Greenland itself, and that there is far too much of water which is being produced by this melting ice. So what it shows based on, so this is based on satellite observations. In reality, what it shows for the ice balance is that it is a very heterogeneous process. So that while there is ice reduction in the southern part of Greenland and ice is really melting, in reality, in the northern part, the ice is growing. And this goes through different atmospheric processes, but also that the reduction in the ice sheet is not only by basal melting, but it also reflects ice sliding based on lubrication at the base of the ice, at the contact between the bedrock and ice. And it is also influenced by the existence of under ice river flow, because the topography of the rocks below the ice is not uniform. So the recent study, when we try to estimate what is the geothermal heat flux, are shown here on the right. And geothermal heat flux is the flux which is produced by the mantle material, which is upwelling and which can produce even melting of the ice and also magmatism and things like this. So the red line, the black line here shows the age of the ice sheet. And even though you can clearly see the location of the Iceland hotspot track, which corresponds to many of the previous results, what is important here is that the melting zone with these absolutely extreme values of heat flow, which require convection, advective heat transfer, shallow magma chambers, and things like this, it lies entirely outside of the ice sheet. which means that Greenland loses the ice mass at the surface through the atmospheric effects, not through the basal melting. If we now switch to Antarctica, so the situation is slightly different. And if you remember, there was results which I showed you from Jerry Mitrovic, which refer to exactly melting over the West Antarctic ice sheet. You can understand how important it is. And many authors, in particular glaciologists, they provide analogs between the events happening in Antarctica and the events in North Atlantic. In particular, in North Atlantic, it is known that there are episodic massive break-offs of large ice masses. They happen every few thousand years. They're caused by the warming at the base of the ice sheet, and this produces some melt water, which works as a slippery lubricant, so that the ice sheet starts sliding and drops into the water. And the onset of this ice break-off can be extremely fast on the time scale of years. So there is really a hot problem. And this small map shows the topography under ice. So it's clear that if you have ice melting, which is here on the tops of the mountains, so that it will be sliding down, and all of these black lines show the under ice rivers, which will take away and carry down the ice sheet. You can also see why West Antarctica is such an important play in this game, because if anything melts on the side of East Antarctica, it will go down to the western side. Again, similar to Greenland, the existing models are highly controversial. They're coming from very, very different geophysical approaches. Color scale is the same, and they disagree between themselves, and they also disagree with glaciological ice drilling models. But you need to have in mind that these glaciological models are very local, so they do not provide continent scale pattern. So this is how the predicted heat flux looks. This is the map on the left. So everything which is red shows the places where the ice melts from below. And the map on the right shows satellite data for the loss of ice by sliding. Green areas where the ice is gained, and red where it is lost. So you can see that there is a general agreement between the two types of maps, even though they actually show different things. But the pattern is quite similar. So there are lots of things happening here in West Antarctica. And if you compare the results for Antarctica and Greenland, you can see the dramatic difference. As I said, in Greenland, everything which is hot is outside of the ice sheet, so that ice sheet is just melting from the top. And in Greenland, the ice sheet is melting from the bottom. And it's definitely is prone to slide down into the ocean. So these results for Antarctica for the mantle heat flow are also consistent with a completely different approach which we used to analyze the structure of the Antarctica continent, where we concluded that the Antarctica continent is substantially smaller than it is usually believed, so that the green part of Antarctica is Beckert Basin. It is similar to the Sea of Japan, and the Antarctica continent proper is only this yellow part. And on the left side, we have the volcanic arc, which is associated with the Paleopacific subduction below the Antarctica continent. So as I said, it is very similar to what we observe in the Japan Sea. It's just that it's turned by 180 degrees. So if we have mantle melting, it may have impact not only on the ice sheets, but it also produces mineral resources. So that the good question is, well, first of all, why mineral resources are important. It is a very naive slide. It doesn't require any actual comments from me, but it shows that, well, because of the technology advancement, we need more and more different elements. So what we needed with the old telephones now more than double in number, and it also includes some exotic elements. So we need mining. And this is another example which shows that how efficiently mineral resources are used by many countries. So, for example, China used more cement over 3 years than the United States used in the entire 20th century. And this is an illustration for this photo of Shanghai made in 1987. And now it is photo taken basically from the same location in 2013. You can see that this is the old harbor station in both photos. So it is exactly the same location. So it is truly amazing. Okay, so how, well, where do we go to find mineral resources? So in most cases, mineral resources or deposits are produced by subduction systems, and you need to think that they are not only young, they can also be extinct. So the question is how to find them. So then there are also deposits in the ancient cores of the continents, termed cratons. Then there are also hotspots associated with mantle plumes, and then there can be other effects, such, for example, like meteorite impact. So this is an example of how ore deposits look in ancient cratonic lithosphere. And I want to emphasize that when we speak about ancient continents, well, these are all colors on this map except for red. So that we're speaking about, well, more than 1/2 of the area of the continents, and many of them are unique due to the irreversible circular cooling, so that the lithosphere, which is in those locations, really has very unusual characteristics. So this is how one of the geophysical models looks for South Africa, and it has huge amount of really unique deposits, in particular associated with gold, uranium, platinum group. It is also all punched by kimberlite pipes. And you can see that there is definitely preference for these deposits where they want to be located and where they prefer not to be located. So that all of them seem to be associated with the ages of the pristine ancient lithosphere. I also mentioned to you that lots of deposits are associated with subduction zones, and in particular with the paleosubduction zones. The most interesting one is the Alpine Himalayan Tetian orogenic belt, which extends from Asia across Tibet, across countries here in the middle, which includes Pakistan, Afghanistan, Iran. Then it goes to the Caucasus, Turkey, and then it continues to the Alpine orogeny and Western Europe. And all of them are related to the closure of the Tatian Ocean, located here, and it was a multi-stage process. So therefore, there were several paleosubduction systems which were created, shown here by different colors. And it is clear that it is one of the primary interests in terms of mineral exploration. I do not have any interesting images for the Tetian belt, but I wanted to show you some examples from the Baltic Shield, because Baltic Shield is very old. It is made out of terrains of different ages. Different colors here to show different ages with a huge span. And all of the black boxes here, they show regions which are probably associated with either paleosubductions or plume events. And they all contain very famous mining districts. So in one of such districts, we made a seismic profile, which was published last year. And here we demonstrated that in this specific region, there is a high velocity, high density material, which is located below the crust. And we interpret this material, this layer, to originate from metamorphic reactions, which are associated with the ancient subduction systems. There was one system which was acting on the southern side. There was another system which was actually two systems which were acting on the northern side, and the result of this is that the subduction system are possibly responsible for creation of this major ore-bearing province in southern Sweden. So with this, I would like to finish my talk. I think that you found something interesting there, and as the final words, I would like to say that it is important that we all use all of the data which is available to us, that we integrate it, discuss with our colleagues, that we challenge common knowledge, and that we simply enjoy what we're doing, we enjoy our work, and we are successful in everything which we start and complete. Thank you very much.
Okay, thank you very much, Irina, for this really wonderful talk. And then we're open for questions. Please put your questions in the Q&A panel while we're waiting. Okay, so there's a question by Rebecca. Thanks a lot for the wonderful talk. You talk about the melting of the pole ice due to tectonics. Is the impact of this melting comparable to the one produced by global warming? Thanks.
Well, it's a very good question. Frankly speaking, I do not have the complete answer to this because I don't know how much of ice is reduced by the global warming. And I believe that it is a continuous process which takes a substantial amount from the surface. But here, when we speak about basal melting, the major point here is that you do not melt just small amount, but you create lubrication by molten water and molten material at the contact between the ice sheet and the bedrock. So that once you melt, it's not a big amount, but then suddenly you can simply detach huge piece of ice melt, of ice sheet. And this way, it's not just a continuous process, but an abrupt change in the total volume. So it has completely different consequences.
Okay, thank you. Waiting for other questions. Maybe I can ask a question. Yeah. Oh, well, Tamara, you can ask.
I'm sorry, I posted it in the chat. I can also ask it directly. My question was, I will just read it out. What are the key components of your numerical models, equations, methods? What programming language do you use to construct it? And as an example now, the most general or common that I would think of is, for example, if you wanted to simulate the development of the continents or their locations due to plate tectonics over millions of years, not only like to look into the past, but only into the future.
Thank you. Well, your question is really overwhelming. It just covers basically my field of geophysics. But in simple terms, the answer to this is that, well, I'm not making any time-dependent modeling myself. So I am trying to determine what is the snapshot of the present deep structure of the planet. And this obviously relates to various types of processes. And then you can start speculating, okay, if now it looks like this, and you assume that in the past it looked different, then which type of processes are responsible for this? And then you also, because we live on the planet which is changing all of the time, we have rocks at the surface of different ages. So we know from geology how one or another particular environment could have been created and which processes create different types of rocks. So you simply can make analogs. So, you determine one region which is young and you see some specific features there. And then you compare them with something which is old, ancient, and where you know how it has been formed. And then you assume that, okay, you have point 1, you have point 2, and then you need to invent some kind of physical and chemical process which can modify and convert system from one position to another position. So for this, I'm using all of the data which I can reach. And as I tried to show on my last slide, and it includes everything which is coming from all different branches of geophysics. It also includes everything which is published by geochemistry, because you cannot understand the nature of rocks and the nature of processes if you do not look into geochemistry. And then obviously surface observations from geology provide very important constraints to all of this. And then basically your question, how we analyze all of these processes, there is a huge area which is geodynamics, where people are writing evolutionary codes and consider, try to reconstruct plate tectonics evolution, try to mimic formation of, different collisional belts or, spreading at mid-ocean ridges. And obviously all of this also includes data which is coming from rock physics and from experimental laboratory studies. And there is a lot of specifics here, because in many cases we speak about processes which require very high temperatures, and they also require very high pressures. And it is extremely complicated to mimic such processes, in particular on the real materials, rock materials, in laboratory. so that many of such experiments are really extremely complicated, very expensive, and time-consuming, energy-consuming. And well, I'm not doing, for example, the core, but for those geophysicists who are working on the structure of the core, you have such an immense pressures that actually many of them can be created only during time scale like seconds. So then, what it means in practice means that then you also introduce another unknown component, because your rock measurements are coming on a very short scales. And what we speak in geological disciplines is processes which operate on extremely long time scales. And the duration is a very important thing, and it simply cannot be mimicked by any way in the laboratory. So, for example, there is a very famous process to explain subsidence of many regions, in particular, which is important, for example, for oil and gas bearing basins. And it is known that it requires, specific conditions. And the best way it can be mimicked is on the order of, in laboratory, on the order of a few months. But in nature, it takes tens or hundreds of millions of years. So how can you jump over such a range? So there is a lot of simplification, obviously, when we do such things. I think that I answered some part of your question.
Yeah, thank you. That helped a lot.
Thank you very much. Maybe I have time for one quick last question, which is what is the relative difference in sea level change in North America versus the Eurasia that you pointed out? What's the strength of the effect?
Well, I don't remember the exact number, but I think that we speak about something like plus minus 30 centimeters.
Okay.
But for many coastal areas, it is quite important. I actually think that I also saw some numbers on the order of 1 or 2 meters, but it's all assumptions driven.
Okay, so
because clearly, it depends, for example, how much of ice sheet you put into the water.
Sure. Yes, but we definitely see the significance of your field of research to the world population and the current political discussion. Okay. If there are no further questions, let me thank Irina again also for the discussion, and I will hand over.